Welcome back. Now we're going to look at some techniques that we can use to characterize solid amorphous dispersions. I should say before we start, there are other techniques that you might use. This is not an exhaustive list. It's just the ones that I think are really good for amorphous materials, and they are the ones that we use in the lab. So it seems kind of sensible to give you examples of the types of things that we actually use when we characterize amorphous materials. Okay. So the first one we're going to look at is Ramen mapping. Ramen, as I'm sure you know, is a type of spectroscopy, and it's a laser-based spectroscopy. So you have a laser shining onto your system. Some of that laser energy is absorbed by the molecules in your system, and some is reflected back as it's after it's interacted with the molecules. And so the laser shines down and is reflected back, and you look for the changes in absorbance in the laser because it's correlated to what molecules are in your system. It's kind of an interesting technique because, being laser based, you can point the laser at a specific point on the surface of your material. And if your material is all the same, when you get the laser back again and you see what has been absorbed, if you move the laser to a different point on the surface of the material, it should always be the same. So as you move the laser beam around, you're just getting copies of the same spectrum. On the other hand, if your material is heterogeneous, and so different regions contain different molecules or different proportions of molecules, as you move the laser around the surface of the material, you'll get different spectra depending on what material is interacting with the laser. And so you can use that as the basis of a mapping technique, because you simply take the laser and then you move the laser across the surface of your material in a regular pattern. There's no real point trying to just randomly put the laser on your material, because you're just going to get a really blurry image. But if you go across it in a raster pattern, backwards and forwards, and you plot the data afterwards, you'll get a sort of map, a visual map of what your material is looking like. And that's how we characterize some of our materials. So this is showing you some data for a 3D printed tablet. I think I've talked about this before, but you may not have seen those lectures. So we asked some students, MSc students of course, as ever, to design and print some tablets that contain two different drugs. And we said to them, think about a way in which you might control the dissolution kinetics of those two drugs. We want one type of formulation where both drugs are released at the same time, and we want another one which we get one drug coming out first and the second drug coming out a bit later. And these were the designs the student came up with. On the left is a multi-layer design. So one drug is contained in the blue layer, one drug is contained in the white layer. And on the right is a core and shell. Again, one drug in the blue, one in the white. I think you might imagine that when you do the dissolution testing, the multi-layer tablet will release both drugs at the same time, because drugs are exposed equally to the solvent. And when you do the core and the shell, the drug in the core comes out after the drug in the shell. So pretty good. A pretty good design, and that is actually what happened when we measured those for real. So as part of that student's work, we wanted to know where actually is the drug in the tablets that you've printed. They were made with 3D printing. So to do that, we took the printed capsules, which are sort of this way, and we cut them in half. And then what we did is we imaged the cross section. So imagine you've got a cylinder like this for the product, you cut it in half, the cross section is a circle. So we then imaged that circle with the Ramen microscope, raster pattern backwards and forwards, because we knew what the two drugs were. One of them was caffeine and one was paracetamol. You can take reference Ramen spectra for paracetamol and caffeine, and that allows you to color code the image, because essentially what you say to the software is, I want you to measure the spectrum at this particular point, and then I want you to tell me, does it match paracetamol or does it match caffeine? If it matches paracetamol, then give it a red pixel. If it matches caffeine, give it a green pixel. And that's the way that you characterize material with Ramen mapping. So you can see the images to the sides of the slides. The images on the top, the sort of purpley images, are a visual image of what the system looked like under the Ramen spectrometer, and the images at the bottom are the color-coded ones against the reference patterns. And you can see on the left you've got the multi-layer system, paracetamol in red, caffeine in green. You can see the drugs are in discrete layers, and on the right you can see that the paracetamol is in the core and the caffeine is around the outside. So it's a really useful way of saying this is where my drug is existing in my system. It's not so great actually for determining what's the difference between a solid solution and a solid suspension. We happen to make solid solutions in this case, and so the individual layers are relatively continuous. But had you made a solid suspension, you need the particles to be big enough that the ramen can actually individually focus on a particle. If it can't, you won't be able to distinguish between particles and molecules, and you need to move to something a bit more complicated like confocal microscopy, for instance. One of the reasons we're not talking about confocal microscopy is in order to get it to work, it picks up fluorescence, and so you have to add something to your system which is going to fluoresce in order to make it visible to the confocal microscope. Another method that we might use is atomic force microscopy. So in atomic force microscopy, you have a really, really fine tip, almost an atomically thin tip, and you bring that tip down onto the surface of your material. There is a laser that shines from the instrument to a mirror on the back of this tip. This is called a cantilever tip actually. So you've got this cantilever like this with a tip on the end. So you put this material, a tip on your material, the laser shines on this mirror and is reflected back to a detector. The reason you do that is because when you want to image something, you move the tip across the surface of your sample, and it will go up and down depending on the surface topography of your sample. And what that will mean is the position of the mirror is moving, and it will change the position of the laser beam on the detector, and it will magnify it because a small movement here corresponds to a big movement on the detector. So you move the tip across the surface of your material in an X and Y direction, and you measure the Z with the laser. And so because you do that, you can build up a topographical image of your sample. If you use a specially derivatized tip, as shown on the screen, you can also do some other things. So one of the things these tips do is they measure thermal conductivity of the material. They do that because by passing a current through that tip, you can maintain the tip at a specific temperature. If your tip is sitting on a material with very poor thermal conductivity, none of the heat is being taken away from the tip. So to maintain the tip at a particular temperature, you don't need much energy because the material isn't moving it. If, on the other hand, you had your tip on a material which had a very high thermal conductivity, like a metal or something like that, that material is constantly removing energy from the tip because it's got high thermal conductivity. So to maintain the tip at a constant temperature, you have to put more energy through it because the material is constantly removing it. So you can measure the thermal conductivity of the material under the tip by seeing how much energy needs to be put through this tip to maintain it at constant temperature. And thermal conductivity is kind of interesting because most drugs, being small molecular weight crystalline materials, have different thermal conductivities from polymers, which are large molecular weight amorphous materials. So you can map on the basis of topography, but you can also map on the basis of thermal conductivity. So an example is shown on the screen. Image to the right hand side is a topographical image of a mixture of indomethacin dispersed in a polymer. So topographical means the surface features, heights in this case of the material. You can see that in the main it's relatively flat. Where the colour changes to a sort of lighter yellow, it's indicating a higher Z position. So it kind of looks like a lot of that material is reasonably flat, and at one point you've got a sort of lump sticking out of it towards the back. If you then do a thermal conductivity map of the same section of the solid amorphous dispersion, that's shown as the square towards the bottom, now you can see that where that lump was corresponds to the dark brown section on that image, and the reason is because that part of your system has a different thermal conductivity from the rest. And what that's kind of telling you is it's likely, but not definitive, but likely at least, that the majority of the surface of your material is a polymer, and that one area where you've got something sticking up is likely to be something else, in this case a drug. So it's kind of suggesting that there's an indomethacin particle exposed at the surface of an otherwise polymeric material. That's kind of cool, but there's one other thing that you can do with a microthermoanalysis probe like this. Not only can you pass a current through the tip to maintain it at a particular temperature, you can also pass a current through the tip to make it rise in temperature. If you make the tip rise in temperature, you're effectively doing a degree of thermal analysis. The way this works is you put the tip on the surface of your material where you want to understand what the material is. You put more current through the tip to raise the temperature of that tip. When the temperature of the tip gets to the melting point of the material upon which it is sitting, the material below the tip will melt and the tip will then drop into your sample. So the way this works is bring the tip along, put it on a particular point of your sample, raise the temperature of the tip, measure the point at which the Z direction changes and the tip drops into the material. And that will tell you the melting point of the material at this point. So on the screen as an example, it's still an indomethacin and polymer mixture, just it's two regions of the surface of a material. I hope you can see that in the top image it looks rather crystalline. I say many times, but crystalline materials are quite easy to see visually because they generally have sharp edges and they look like crystals, whereas amorphous materials tend to be rather smooth. So the image on the top looks as though you've got quite a lot of crystals and only a very small amount of smooth surface, and the image on the bottom you've got a lot of smooth surface and a very small amount of crystalline. Where it says LTA, LTA stands for Localized Thermal Analysis. So they are regions where the tip was moved over that sample, was placed on the sample and the temperature was raised, and we're measuring the temperature at which the material softens and the tip drops into the material below. Those are the images to the right of the topographical images. So I hope you can see, if we consider the top one first, LTA 1 and 3, so that's the black and the green, they both show melting at a relatively high temperature, 160 degrees, and LTA 2 shows melting at a much lower temperature, around about 65 degrees. If you look at the images to the left, you can see that LTA 1 and 3 are sitting on what looks like crystalline material, and LTA 2 is sitting on what looks like amorphous material. So that's a way of sort of verifying that the smooth is amorphous and what looks like crystalline is crystalline. Because you know what the melting temperatures of your indomethacin and the drug polymer are, you can also confirm that the amorphous material is polymer and the crystalline material is indomethacin, so that's kind of handy. The same thing is shown for the image below, it's just that LTA 1 is the only point sitting on what looks like a crystalline material, and LTA 2, 3 and 4 sitting on amorphous material. And again, if you look to the images to the right, you can see that LTAs 1, 2 and 3 are all melting at LTA 2, 3 and 4 are all melting at a low temperature, and LTA 1 is melting at a high temperature, so it's the same thing. So it's allowing you to say, okay, this is what the topography of my material is, this is where I think the drug is, and this is where I think the polymer is, and at the same time you can confirm that by measuring the melting points of the materials at those phases. So it's kind of a handy technique to use. Possibly the most important technique that we use is differential scanning calorimetry. And I say that not because I love calorimetry and think it's the answer to everything, it's because DSC measures phase changes. And if you're following what I said from the start, amorphous solid dispersions are really characterised by phases. We had either a solid suspension, which was 2 phase, or a solid solution, which was 1 phase. Since the DSC is capable of measuring phases, instantly it should tell you the difference between a solid suspension and a solid solution, because it's measuring the number of phases. It's relatively as simple as that. There is another reason, because you might say to me, well, hold on a minute, Simon, X-ray diffraction is the gold standard for physical form determination, so why don't we use that? The answer is because these are amorphous materials, and so by X-ray diffraction the material is going to appear as a halo, so no particular reflections because the material isn't crystalline. And even if the drug particles, not molecules, particles were crystalline, the chances are they're going to be there at a relatively low percentage, and you need at least 5%, 5 to 10% of a material to be crystalline in order for an X-ray diffractometer to see it. So the risk is that you don't see any crystalline material in solid amorphous dispersion with X-ray diffraction, and hence you misinterpret what you've actually made. So a DSC is a much better way, I think, of looking at amorphous materials, and an X-ray diffractometer is a better way of looking at crystalline materials. I think that's a fair way of putting it. I put on here that amorphous materials behave with interesting properties in a DSC. What do I mean by interesting? I mean, When you make a solid amorphous dispersion, the clue's in the name, it's a solid. And so you look at it, you think it's a solid. And your brain is predetermined to believe that solid materials melt. So you take what you believe to be a solid material, you put it into a DSC and you expect it to melt. An amorphous material has no crystalline lattice. If it's a true amorphous material, there's no crystal lattice. As a consequence, there is no lattice energy required to make the material melt, and so it doesn't actually melt. It goes from a high viscosity liquid to a low viscosity liquid. But in that process, there's actually no change in energy of the material, or not, at least not a phase change in the material, because it was a liquid and it's still a liquid. It's the viscosity has changed, but the phase hasn't. It's still a liquid. And so as a consequence, because the DSC is measuring phase changes, you actually don't see a melting point of an amorphous material in a DSC. Okay, so no lattice energy, so no melting point. It really confuses people in the lab that you put in what you believe is a solid material, but you don't see it melt, because when you take it out, it's a liquid, and it's really confusing. So you just have to remember it was a liquid when it went in, and it's still a liquid when it comes out, and therefore there's no phase change, so nothing to see. What you do tend to see in the DSC, however, is a glass transition, a step change at the glass transition temperature, because the material is going from a high viscosity liquid to a low viscosity liquid, and that does have a consequence for the DSC. So it is generally possible to measure the glass transition temperature by a DSC, but you won't measure melting. Sometimes people put amorphous materials into a DSC and they will see a melting point, and it's kind of important to recognise where that material has come from, and I'm going to come back to that in just a minute when we look at an example. So I put on the screen, it might crystallise during heating. It's really important to recognise that heating a material up is giving it energy, and giving it energy is allowing materials to move, and if you allow them to move, they may well crystallise. If they crystallise, they will melt. So you just got to remember, a truly amorphous material won't melt, and if you see a melting in a DSC from a material you believe to be amorphous, you have to be really careful in interpreting where that crystalline material has come from. What does a glass transition temperature look like in a DSC? The answer is it looks like a step. It looks like a step in the DSC baseline. Why? Why have we got this change in baseline? For this, you have to remember how the DSC operates. A DSC has a sample and a reference material, and it is measuring the amount of power which is required to heat both of them in temperature. I am sure you remember that the amount of energy required to raise a material by a certain temperature is the heat capacity. So it's a specific heat capacity is the amount of energy required to raise either 1 gram or 1 mole of a material by 1 degree centigrade. So the heat capacity is how much energy has to be put into a material in order to get it to rise in temperature. The other thing you have to remember about heat capacity is to think to yourself, how is a material using the energy that I'm giving it to go up in temperature? If I'm giving a material energy and the molecules in that material are moving, then when I give it more energy, I make the molecules move faster. In other words, the molecules are using the energy to move around, but the system itself is not necessarily rising in temperature quite so fast. If the material contains molecules that are rigidly held in place, and I apply some energy, those molecules can't really waste that energy by moving around because they're kind of held in place. And so what I'm saying here is a material that's got lots of molecules free to move kind of wastes a lot of the energy that you give it by moving the molecules faster rather than going up in temperature. But a material that contains molecules which are relatively rigidly fixed in place can't waste that energy by moving its molecules faster, and so it goes up in temperature quicker. In other words, the heat capacity of a material with moving molecules tends to be different from the heat capacity of a material with fixed molecules. Because the DSC is measuring the difference in power that's supplied to the sample and the reference should be unchanging. That's the point of it being reference in the first place. So it doesn't matter whether the DSC is plotting sample minus reference or reference minus sample. The reference is constant. But as the sample goes through its glass transition temperature, it's moving from a material where the molecules are sort of rigidly held in place, because it's a high viscosity, right, to a material where the molecules are much more free to move because it's now a low viscosity. So it's gone from high viscosity to low viscosity, or it's gone from one heat capacity to a different heat capacity. A lower heat capacity when it was a high viscosity material to a higher heat capacity when it's a lower viscosity material. And that means that when you plot either sample minus reference or reference minus sample, there will be a step change in the baseline because the heat capacity of your material on the sample side has changed. And that's what we see on the screen in front of you. You see this step change, and it reflects the change in mobility of the molecules as it's gone from a glass to a liquid. And we characterize that step change with the height, which tells us about the heat capacity, and the midpoint of the transition, which corresponds to the glass transition temperature. So what that means is if we have a material which is a true amorphous material and we put it into the DSC at a low temperature below its glass transition temperature and we allow it to heat up in the DSC, we should at some point see this step change in the baseline, which is very characteristic of a glass transition. I can tell you that lots of PhD students on our floor of the pharmaceutics department are very good at spotting glass transition temperatures in materials as they heat them up in the DSC, because that's what they're looking for a small change in the baseline. It's one of those reasons why it's really important when you set up a DSC experiment that you set it up carefully, because you want the baseline of the instrument to be as flat as possible with the least amount of noise, because you're looking for a small change in that baseline. If there's lots of noise, it's really difficult to see. So you have to pay a little bit of attention to how you set up the DSC experiment. On the screen I'm showing you some examples of amorphous material heated up in a DSC. It's the same material, it's just at two different heating rates. I'm going to come back to that in just a second, but focus on the top trace for now. The first thing you see is a step change in the baseline. That's very characteristic of an amorphous material. If that amorphous material did nothing else, it just carried on as a liquid, the rest of that trace would be flat and we would see no peaks. But it's quite common with an amorphous material to see a number of other peaks afterwards. In this case, an exotherm followed by an endotherm. Remember, it's really important in a DSC to specify in which direction the data are being plotted. In this case, exothermic events are being plotted up. And so what that means is the first peak is exothermic and the second one is endothermic. I know I always caution against definitively saying what's going on in a material in a DSC by just saying exothermic means the material is crystallized and endothermic means the material has melted. But in this case, that's exactly what's going on. You started with a material which is a brittle glass, you heated it up and it went through its glass transition temperature. That means the molecules are quite mobile because now it's a low viscosity liquid. Because it's a low viscosity liquid and the molecules can move, the chances are that they will crystallize. And if they crystallize in a DSC, generally it releases energy, and that's exothermic. And so we see this exothermic peak indicating the material has now crystallized. And then as we carry on heating, at some point, because it is now a crystalline material, it will melt. And so we see a melt of that material at a higher temperature. I said earlier, amorphous materials don't melt. And you might say to me, why? Why now am I seeing a melt on the screen when the material was amorphous when it went into the instrument? Surely that shows you amorphous material melts. The answer is, and I said this already, you've got to think about where the material became crystalline. When it went into the DSC, it was purely amorphous. It has crystallized during heating because the DSC itself is giving energy to that material and it's allowing it to crystallize because we are providing energy. It was not crystalline when it went into the DSC. It crystallized during the DSC experiment, which is the exotherm, and as a consequence it melted. So therefore it's not wrong to say that an amorphous material doesn't melt, but we have to recognize that an amorphous material may crystallize during a DSC experiment and then melt. But it's the crystalline material which has melted, not the amorphous one. I hope you're okay with that. The bottom line on this graph says fast heating rate. It's the same sample run in the same instrument, it's just a faster heating rate. And I put this here simply to show you that if you're trying to characterize a material with a DSC, sometimes it can be really useful to run the same sample at two different heating rates. I try and encourage all the PhD students to do this. And the reason is because if you're trying to assert that a step change in the baseline is a glass transition temperature, One thing you can do is run it at 2 different heating rates, and if it's truly a glass transition temperature, the temperature at which the step change appears should appear at a higher temperature with faster heating rates. The same is true for crystallization actually. If you're asserting that an exothermic peak is crystallization, if you run the same material in the same DSC at a faster heating rate, the temperature at which you see the material crystallize should be at a higher temperature. And if you look at this graph, both the glass transition and the crystallization have moved to higher temperatures. I could talk about why that is, but it would take a long time in this lecture, so I just really want you to focus on the fact that this happens, and if you're interested in why, we can have an offline conversation about it, okay? So just for now, remember that as you increase the heating rate, a glass transition temperature or a crystallization temperature should appear to higher temperature. A melting, on the other hand, does not show temperature rate dependence, and so it doesn't matter what your heating rate is, the material should always melt at the same temperature. And so again, in this particular instance, the 2 materials melt at the same temperature. So it's just a good way of confirming that the first peak is a glass transition temperature, the second one is crystallization, and the third one is actually melting. Now, why are amorphous materials tricky to study by DSC? The answer is because they relax with time. We looked at that already. You had the graph. The arrow number 1 was the material relaxing with time. That means that the molecules are starting to become aligned, and as they become aligned, they're losing energy, and so they go down on the graph. So the graph, which is now on the screen in front of you, we also had another arrow number 2, and I said this becomes important during DSC, and I'll explain later. And the reason it's important is because this graph is showing you the formation of an amorphous material, so starting as a liquid, supercooled liquid, forming a glass, annealing at a particular temperature, and in annealing, the material is losing energy and it's going down arrow number 1. When you put that material into a DSC pan and you press on and you start to heat the DSC up, the material is at the bottom of arrow number 1, as shown on this graph. And so as you start to heat it up in the DSC, it will follow the arrow, the horizontal arrow, increasing in temperature. Okay? When the material gets to its glass transition temperature, it's moving from a high viscosity liquid to a low viscosity liquid. Another way of thinking about this is, on storage, the molecules are relaxed, but because it's a viscous material, it's kind of stuck in this relaxed state. When you heat it up in a DSC and you go through the glass transition temperature, it becomes a low viscosity liquid. Instantly, the material will revert to where it was on the supercooled liquid line when it was being formed, and so the material jumps from the end of that arrow going up arrow number 2, back to where it would have been as it was being formed. That's a really complicated concept to get in your mind, and I propose, if you're not quite following, just stop the video, rewind, play again, just to run that through in your head so you kind of get what I'm saying here. That on one side of the glass transition temperature, the material is low viscosity liquid, and on the other side it's a high viscosity liquid. So what that means is the material, the molecules can be in numerous different places, but they move there really slowly or fast, depending on whether it's a high viscosity or low viscosity. At point number 1 on that graph, the material is slowly organising itself as it relaxes, but it's still a high viscosity liquid, and so it can't respond rapidly to changes in temperature. When we increase the temperature in the DSC, the material changes slightly but very slowly until we get to the glass transition temperature, at which the material suddenly reverts back to being a low viscosity liquid. And because it's now a low viscosity liquid, the molecules can move, they're free to move, and they will go back to where they were had we been on the supercooled liquid line in the first place. And the consequence of that is, in arrow number 2 going up, the material suddenly gains energy. I know I've said many times that in nature material can't spontaneously gain energy, but this is not spontaneous. The material is in a DSC, and the DSC is providing power, and that power is being provided to maintain the material at a constant temperature. And so if the material does something where it sucks energy in, the instrument's providing it, and so the material will jump up at point number 2 and it will go back to the supercooled liquid line as shown on the diagram. And this has a number of consequences for the DSC trace. One of those consequences is shown on the screen in front of you. If you run an amorphous material that's aged So it's been on storage and it's been allowed to relax. In the DSC, you don't see a simple glass transition step like this. You see a rather complicated looking thing like this. And one of the questions is, why? The answer is because that trace represents two things. The glass transition itself, plus the energy that the material is absorbing as it goes up that arrow, point number 2 on the graph that I just showed you. So it's a sum of this plus this. And so we get this, which is the line that's shown heating rate number 1. It's really characteristic for an aged glass, actually, that you don't see a clean glass transition. You see a rather complicated looking glass transition because you've got this energy of recovery, it's called. So you see this recovery energy as well as the glass transition temperature. If you heat a glass in a DSC like this and you see that type of event, if you stop heating just after that glass transition temperature and you cool back down, the material will go back through its glass transition and become a high viscosity liquid again. When you then reheat, now the material hasn't had time to age, has it? It's been heated up, it's gone through its glass transition temperature, it's recovered that energy that it lost on storage, you've cooled it back down again. Effectively, it's a freshly created glass. If you then reheat it, so just in your mind here, we're heating, cooling and heating again. The material hasn't had time to relax, and as a consequence, on the second heating, there is no enthalpy to recover, and so you just see a clean glass transition again, which is shown on the screen. So I suppose what I'm saying here is, when you're running a DSC experiment to try and understand the properties of an amorphous material, you've got to be kind of clever in the way that you set up your DSC experiment, because changing the heating rate or going through a glass transition temperature, stopping, cooling and going through it again, they're all really good ways of demonstrating has the material relaxed. Is it a true glass transition temperature and things like that. Most of the students, in my experience, run one DSC. They take their material, run the DSC, go off and do something else. And then they come back and they try and analyse the data towards the end of their project. And they realise at that point, they can't truly say, is this a glass transition temperature? Is it a crystallisation event? Because they haven't really interrogated the system. And you can interrogate the system by reheating the sample and also by heat-cool heat at specific points. So just bear that in mind if you're ever using a DSC to characterise an amorphous material. There is one other thing that you can do with a DSC, and it's really complicated, so I'm going to show you an example, but we're not going to go through the mathematical analysis. You can read it up on the internet if you wish. And that is that when you've got an aged glass and it does this, I said already, it's the sum of two things, an enthalpy of relaxation and a glass transition temperature. We have a special type of DSC called a Modulated Temperature Dsc, and it allows you to separate those two events from each other. It's really complicated, and I don't propose right now to go through why that is. If we have a workshop later in the term, I'm happy to talk through it at the workshop, or you can read around it and ask me some questions. But just for now, you just have to accept that this is what happens. So in a normal DSC, the heating rate that the instrument is applying to your sample is linear. So 10 degrees per minute, 20 degrees a minute, whatever it is, it's a constant heating rate. In a modulated temperature DSC, you multiply your heating rate by a mathematical function. It's usually a sine function. And the consequence of that is, rather than having a linear heating rate shown on the screen with a dotted line, you have a sinusoidal heating rate, which is a little bit complicated. And you can use mathematics to separate events which are thermodynamic from events which are kinetic. I do not, at this point, wish to get into the really complicated discussion about what's a thermodynamic event and what's a kinetic event. For now, it suffices to say that glass transition is a kinetic event and the enthalpy of recovery is a thermodynamic event. And because that's the case, if you run one of these materials in a modulated DSC experiment, you can separate those two heat flows and you will end up with something that looks like the graphs on the screen in front of you. This was a real amorphous material run in the modulated DSC by myself in my own laboratory. And there are a number of things on here which are shown, which is really complicated, and I don't want you to get bogged down in it. It's just that the solid line, which says total power, is reflective of the DSC trace that you would measure in a normal DSC for an aged glass material. You can see it's very complicated. It's got a bit of a bulge like this and then a peak and so on. It's really difficult to say for certain that that is a glass transition going on there. And what was actually happening is the material was wet, So there was an endotherm because the water was evaporating from the sample, plus it was an aged glass. So there was a glass transition temperature and there was an enthalpy of recovery. When we ran it in the modulated DSC, the water loss and the enthalpy of recovery are both thermodynamic events, or in the terminology of our modulated DSC, that means a non-reversing signal, or a one-way process, and they appear in the non-reversing signal. So if you look at the signal at the top, the one with the very widely spaced dots, you can see the water loss and the enthalpy of recovery. But the glass transition temperature is a kinetic event, and it appears in what's called the reversing signal. Now you can see a much clearer glass transition in the reversing signal. And if you add the two dotted lines together, you end up with a total power signal. So I don't really want to focus on that too much right now. I think if you end up doing a project on amorphous materials and you end up characterizing with modulated DSC, then I think we can talk about it a bit more. But for now, I just want you to remember the basic principle that if you run an amorphous material in a modulated DSC instrument, you can pull out the true glass transition temperature to confirm that the material is truly amorphous. So the last thing is, how would we use DSC to look at a real solid amorphous dispersion? The answer is, it's very simple. Just take your amorphous dispersion, put it in a pan, heat it up in the DSC and see what happens. The tricky bit is that you've got to look at the peaks and interpret them properly. In very simple terms, if your material is a solid solution, a purely amorphous solid solution, you're probably going to see a glass transition and nothing else. Nothing else should happen. There's no phases to melt. The DSC is looking at phase changes, and you've only got one phase, which is the amorphous polymer phase with drug molecularly dispersed in it. So you should just see a pure glass transition temperature, no melt of the drug. If it's a solid suspension and the drug particles are crystalline, then when you heat that up in a DSC, you should see a glass transition temperature for the polymer, plus you should see melt of the crystalline phase of the drug. Okay. In fact, it's a really good way of saying that material is a solid suspension with crystalline drug particles, is you still see the drug melt in the solid phase. If it was a solid suspension and it had amorphous drug particles in an amorphous polymer phase, in principle you should see two glass transition temperatures, one for the polymer phase and one for the drug phase. So in basic simple terms, a solid solution should give you just one glass transition temperature. A solid suspension with crystalline drug particles should give you a glass transition temperature plus a melt for the drug. And a solid suspension with amorphous drug particles should give you two glass transition temperatures, one for the polymer and one for the drug particle. In practice, I think you might imagine that that's not quite as simple as that. And it's not quite as simple as that because the material can change on heating. And I've given you an example already, which is that a material can crystallise on heating. But it's really important, if the material crystallises on heating, you should see that. So there should be an exotherm before any endotherm. So just seeing an exotherm on heating of one of these materials should give you a red flag in your mind that the material is changing on heating. And so you need to interpret the data really carefully. Final thing in the lecture is just to give you an example of a real solid amorphous dispersion, which was made by one of our students. It's a olanzapine in PLGA. It turned out to be a fantastically interesting system, and the student published a number of really good papers on it, which I highly recommend you have a look at. But I think if you were making a solid amorphous dispersion and you were looking to characterise it by DSC and you saw some data like this, your heart might sink because there's a lot going on very clearly. And also very clearly you can see an exotherm. You can't really see a TG, I've got to say, in there. There might be one, but it's quite difficult to see. You can see an exotherm, you can see an endotherm, and if you look closely at that endotherm, it looks like there are two elements to that endotherm. So the student did loads of work. I mean, he did a whole PhD on this system, so it's not an easy thing to interpret, but he did a whole load of work on this system. And one of the things he did was temperature controlled X-ray diffraction, so you can measure the powder patterns of this material at various temperatures. So on the screen shows you the powder patterns at 65, 120, 180 and 196 degrees centigrade. If you look back at the DSC trace, I hope you can see that that corresponds to before that exotherm, after that exotherm, before the first melt and before the second melt. And you can see that the material, it started with a broad halo with some peaks. So the inference from that is it was partially crystalline to start with, but in the main it was amorphous. By 120 degrees, so that is after that exotherm, the material is clearly crystalline, which helps confirm that the material did crystallise. The exotherm is a crystallization event. At 180 degrees, which is roughly where the first one of those melting peaks is, the material will change form again. Chances are, at 120 it was actually a mixture of polymorphs, and the lower melting polymorph melted at 180, leaving behind the second polymorph, and then at 196, which is after the second peak, the whole material had gone back to amorphous again because the material is now a liquid. What's the take-home story from this? The take-home story is that DSC is fantastically simple to use for putting in amorphous solid dispersions, but amazingly difficult to interpret if you don't go through and measure some other data at the same time. And we've done a whole load of work looking at how you can use X-ray diffraction to help you interrogate and understand amorphous dispersions when studied by DSC, but that's a topic for another day. What does this mean? It means we're at the end, and therefore I can summarise the things that you need to remember. Solid amorphous dispersions can be solid solutions or solid suspensions. Solid solution is 2 components, 1 phase, because the drug is molecularly dispersed. Solid suspension, 2 component, 2 phase, because 1 phase is polymer and 1 is drug. And you need to remember that the drug particles can be amorphous or crystalline. So there are 3 basic types of solid amorphous dispersion. It's important to understand which one you got, because that will impact how the material is going to behave on storage. Relatively clearly, I think, if the drug particles are crystalline in a solid suspension, that's probably a good system for stability. The drug is crystalline, so should be stable, and the polymer is unlikely to crystallise, so that should be good. If you've got amorphous drug particles in a solid suspension, the risk is they will crystallise on storage, and if you've got solid solution, the risk is that the drug will crystallise on storage. So the material is constantly changing, and you've got to recognise that with amorphous materials. How can you characterise them? You can characterise them with Ramen Mapping, which is simply going to show you what phase is where. You can do microthermal analysis, which is showing you surface topography, and it's also allowing you to determine by melting what phase is where. And you can do DSC, which frankly will show you all the phases that are in a material, but you have to recognise that some of those phases may actually have been created by heating during the DSC in the first place, and so it's a pretty good idea to use X-ray diffraction to help convince yourself what is actually going on. With that, we are done, and hopefully I will see you in a workshop where we can talk about some of this stuff later in the term.